Hello students, Jai Swaminarayan. This is Professor Urvish Mewada, HOD Electrical Department, Sri Swaminarayan Institute of Technology, Bhat Gandhinagar. I am the subject matter of Power System 2, which is in the 5th semester, Electrical Department, and GTU subject code for this subject is 3150911. Students, this is the 4th lecture for unit number 3 for Power System 2 and chapter number 3. The chapter number 3 that we are conducting is transmission line modeling and performance. Now we are discussing the topic number 4, medium transmission line, and in the subtopic 2 for the for the topic number 4 is nominal T method. Now let us discuss this analysis of power system transmission line using nominal T method. Now, why this method is called nominal T method? First of all, so we are considering or we have divided transmission line in two part with the help of capacitor in between. So this is the capacitor which is considered in the transmission line at the middle of the transmission line. This capacitance is considered. That's why this is forming the T. So that's why this is called the nominal T method. So in this method, the whole line capacitance is assumed to be concentrated at the middle point of the line. That's why it is called the nominal T method. Now this is the sending end side and this is the receiving end side. Sending end side current is Is, and the resistances and reactances both are divided in two part. So R will become R by 2 and X will become XL by 2, and Is is the sending end current, and V1 that we get across the capacitor over here. So this is the voltage across capacitor C, and VR is the receiving end voltage across the load, and IR is the receiving end current. So here we considered one line and one means we can say one line and one is neutral, so means two wire in between we are measuring the capacitance. So the uh, in this method in this method arrangement, full charging current flows over half the line that figure shows here, and one phase of three-phase transmission line is shown, and as it is advantageous to work in phase instead of the line to line, so that's why here we considered one phase and one neutral. This is the phasor diagram for this particular circuit. So here let us discuss the phasor diagram first. So in the phasor diagram, the construction of the phasor diagram, you can see over here VR is taken as a reference. So note that the construction of the phasor diagram, this VR is taken as the reference phasor, uh, and it is represented by the OA, the load current IR, uh, lags behind VR by phi R, and the drop AB over here is equal to IR into IR is the receiving end current into R by 2 in phase with the IR over here you can see, and the BC is equal to, this is the BC, this BC is equal to IR into XL by 2 that leads the IR by 90 degree, and the phasor OC, this phasor OC represents the voltage V1 across the condenser means capacitor C, and the capacitor IC means capacitor current IC leads V1. This capacitor this is the V1, and this is the IC which is leading, means in this direction, V1 by the 90 degree as shown in this phasor diagram, and the phasor sum of IR and IC, this IR and IC is the is gives the value of sending end current Is. uh, and now CD means after the point CD indicates that the CD is equal to Is into R by 2 in phase with the Is. So this loss is in parallel with this Is because this is the resistive loss, and while DE is equal to Is into XL by 2, that leads IS by 90 degree. Then this OE represents the sending end voltage VS. So this is how we can explain the phasor diagram of any circuit. So let us discuss elements of the circuit again. IR is the load current per phase. XL is the inductive reactance per phase. Cos phi r is the receiving end power factor, which is lagging always. Why it is lagging? Because we have not considered any capacitor in series with the circuit, that's why it is lagging. And then V1 is the voltage across the capacitor. um, One thing you should keep in mind, this capacitance is the imaginary capacitance. This is not physically connected in the circuit. We are considering the effect of capacitor over here. Then C is the capacitance per phase. Vs is the sending end voltage per phase. The phasor diagram of the circuit means this is the shown over here. Now the receiving end voltage, let us start with this analysis. Receiving end voltage Vr is taken as a reference. So again there is no angle, uh, means it is not drawn at any angle, means it is at the reference phase. That's why Vr is equal to phasor voltage Vr is equal to Vr plus J0. Now the load current, load current means receiving end side, that's why load current is IR. So IR is equal to, IR has two component over here. You can see IR has two components, cos phi r and J sin phi r. So IR into cos phi r minus J sin phi r. So this is how we can determine the IR for the nominal T method. Now voltage across the capacitor. So voltage across the capacitor V1, let us see the phasor diagram again. Voltage across the capacitor, this is the V1. So V1 is means V1 found with the help of VR plus IR R by 2, then IR XL by 2. So instead of this resistive and reactive drops, we can write IR Z by 2. So V1 is equal to VR plus IR Z by 2. So over here you can see that VR into IR plus Z by 2. So let us put the value of IR over here. So VR plus IR sorry, VR plus IR into cos phi r minus J sin phi r. And the this impedance is basically it is a composition of R by 2 plus J XL by 2. So that's why this Z by 2 replaced with the R by 2 plus J XL by 2. Now capacitive current IC, so that we know, V means I is equal to V is equal to IR. So this V1 is equal to I into 1 upon XC. So XC is comes over here when we make IC as a subject. So IC is 2 pi means J omega C V1. So this omega C will means replace with the 2 pi F. So J 2 pi FC V1. So the sending end current IS from the phasor diagram, you can see this IS is the IR plus IC. So here it is 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 equal to IR plus IC. Now the sending end voltage VS. So VS is again we can say it is V1 plus VS is equal to V1 plus this means IS into Z by 2. See this VS is a composition of V1 plus IS into Z by 2 from the phasor diagram. So this is the equation for the VS. Now we have the value of VS and VR, so we can find out the percentage voltage regulation and the efficiency from these equations. So let us see the examples relevant to the nominal T method. So here you can see a three-phase 50 hertz overhead transmission line, say 100 kilometer long. So it is above 50 kilometers, so it means it is a medium transmission line, has the following constants. See, you can see the resistance per kilometer per phase is 0.1 ohm, and the inductive reactance per kilometer per phase is 0.2 ohm, and the capacitive susceptance is 0.04 into 10 raised to minus 4 C1. And the data we need to find out from this data given. So determine, first is the sending end current, second is sending end voltage, third is sending end power factor, then the transmission efficiency, uh, when the supplying a balanced load of 1000 kilowatt at 66 kV. So this is at the receiving end, and power factor is zero point 0.8 lagging. We are using the nominal T method, so it is indicated that use nominal T method. This is what will be given in your exam, which method you should apply for the calculation of this example. So read it carefully whenever such kind of example is given, and apply that method accordingly to find out the solution of the given example. So here again we drawn two means first is the circuit diagram, and second one is the phasor diagram that we already discussed in the previous slide. So figure 1 and figure 2 shows the circuit diagram and phasor diagram of the line respectively. So you are aware with this diagram and you are aware with this phasor diagram. So let us start the calculation for this example. So total resistance per phase is given, so that is 0.1. so here we considered the 100 kilometer line, so 0.1 is multiplied with the 100, that's why it is 10 ohm. So for the same XL means inductive reactance, it is 0.2 given. So for per kilometer per phase, so here the 100 kilometer line is considered, so that's why 0.2 into 100, it is 20 ohm. Then the capacitive susceptance Y, so it is 0.04 given into 10 raised to minus 4, it is given. So it is for the 100 kilometer lines, 4 into 10 raised to minus 4 Siemens. Now receiving and voltage per phase, so line to line voltage is given in the data, that is 66 kV. So the for per phase voltage is line to line voltage divided by root 3. So 66 kV divided by root 3 is equal to 38,105 volt. Now the load current, so this is the nothing but the three phase power equation. P is equal to root 3 VR IR cos phi R. So all the terms are known except the IR, so we can place the values of P, then VR, then cos phi R, so we can determine the value of IR from this. So the value of P is that is given, so 1000 into 10 raised to 3, so it is 10,000 into 10 raised to 3, it means it is 10,000 kilowatt. Then root 3 VR is given, that is 66 into 10 raised to 3 means 66 kV. Then the zero point 0.8 is the receiving and power factor cos phi R. So from this we can determine the value of IR, that is 109, means 109 ampere. Then the cos phi R that we know 0 0.8, so we can determine the sin phi R from that, so it is 0.6. Now impedance per phase, so equation of the impedance per phase, so impedance is a composition of the resistive component as well as the reactive component. So R plus JXL, we have the value of R and XL, so we can determine the Z. So R is 10 for the 100 kilometer line, and XL is the 20 for the 100 kilometer line. Means this is the overall resistance and reactance, so from that this is the overall impedance of the circuit. Now we are determining the first, taking receiving and voltage as a reference, that is already we know that we are taking the receiving and voltage as a phasor. So we are taking VR is equal to VR plus J0. So there is no angle because it is taken as a reference. So VR is 38 kV, 38.105 volt, means 38,105 volt, or 38.105 kV. And the load current equation that we know, IR as the two components, cos phi R minus J sin phi R. So IR into cos phi R minus J sin phi R, we have the value of sin phi R and cos phi R and IR. So from that the voltage means from that the current value is 87.2 minus J 65.4 ampere. So this is the load current, means this is the complex value of the load current. Now voltage across C, so from the phasor diagram you can see that voltage across C, so this is the V1, so V1 is VR plus IR into r by 2 and ir xl by 2. Instead of, we can write z, this means over here we can, as we know that this is the z, so vr plus this is the impedance of this triangle. So here is v1 into, v1 is equal to vr plus ir into z by 2. So we have all the values. By placing the values, we will get the value of v1. So the output voltage, means capacitor voltage v1 is 39.195 plus j545. Total is the voltage. This is the total voltage that we are considering across the capacitor when the system is healthy, and we are considering the effect of capacitor at the middle of the line as a nominal T method. Now, charging current, IC is the as we know that V is equal to Z is equal to V upon I. So Y is equal to I by V, means it is the reciprocal. So we have the value of Y, that is given 4 into 10 raised to minus 4 for the 100-kilometer line, and we have the value of V1, that we find out from the previous slide. And by placing the value, we will get IC is equal to 0.218 plus J 15.6. So this is the capacitor current, means across the capacitor current. This is the charging current. Now the sending end current, IS is the combination of IR plus IC that we already seen. Let us see the phasor diagram again. So IS is the addition of IR and IC, so that's why IS is equal to IR plus IC. So by placing the value, we will get the value of IS, that is 100 ampere. This is the data which we found out already. So IR is 87.2 minus J65.4, and the IC is minus 0.218 plus J15.6. Now the sending end voltage VS is the it's a combination of V1 plus IS into Z by 2. We have all the values. By placing the values, we will get the value of VS, that is 40,128 plus J1170. This is the complex form. This is the R angle theta form of the voltage, means sending end voltage is 40,145 at angle means uh, 1 1 into, means 140, 1 degree and 40 voltage. This is the angle at which we are considering the effect of Vs. So line values of sending end voltage uh, is means this is the voltage, is the phase to phase voltage. Now this is the line to line voltage, so it is multiplied with the root 3. So 40,145 multiplied by root 3 is equal to 69,533 volts. So we can write it 69.533 kV. Now referring this phasor diagram again, so over here you can see that this is the receiving end current, this is the sending end current, and this is the VR receiving end voltage, and this is the VS. So from this the angle theta 1 is the angle between VR and VS. So between VR and VS we have the angle is theta 1. So theta 1 is, from this we have already determined, it is 1.40 degree. And then theta 2, it is the angle between VR and IS. So VR and IS, that is already derived 29.47, means 29 degree 29.47 degree, and phi s is the angle between VS and IS. So that's why it is the addition of this two. Phi 1 plus phi 2 is equal to 31.27. So the sending and power factor cos phi s, by putting the value of phi s over here, so this is the cos 31.27, so it is 0.853 lagging. So this is the sending and power factor which is act as 31.27 degree, and that will be 0.853 degree 853 lagging, because we are considering this transmission line as a R plus jx form. That's why the power factor is always lagging. So this is how we can determine the power factor. Now the sending end power. So sending end power is P is equal to 3 VSIS cos phi s. So by placing the value of this, we will get 10,273.105 kilowatt. So this is the power delivered, is 10,000 kilowatt. Now the from this we can determine this is the power delivered and this is the sending end power. So the power delivered means this is the output and this is the input. So this is 10,000 divided by 10,273 0.105 multiplied by 100, so it is 97.34%. so this is how we can determine all the parameters using nominal T method. Let us see one example again. So in this example, the three-phase 50 hertz transmission line 100 km long, that is delivering 20 megawatt of the power at 0.9 power pf lagging, and at 110 kV the resistance and the reactance of the lines per phase are given, that is 0.2 and 0.4. So this is the resistance of the line and this is the 4.4 is the reactance of the line respectively. And while the capacitance admittance is given 2.5 into 10 raised to minus 6 Siemens per kilometer per phase. So calculate first is the current and the voltage at the sending end, means Is and Vs, and sorry, efficiency of the transmission line, means output upon input. So here it is again indicated that you use nominal T method. So again we have drawn this two circuits that we already discussed. This is the circuit diagram and this is the phasor diagram of this particular circuit. So the data given as R is equal to 0.2, so for 100 kilometer that will become 20. XL is 0.4, so for 100 kilometer it will become 40 ohm. So phase impedance is the combination of R plus XL, so R plus JX. So R20 plus J40, this is the impedance of the circuit. Total capacitance admittance that is given 2.5 into 10 raised to minus 6. So for 100 kilometer that will become 2.5 into 10 raised to minus 4 Siemens. Now let us see the receiving end voltage. So receiving end voltage means it is given line to line. So receiving end voltage per phase is 110 into 10 raised to minus 3. So divide by root 3, so that will become 63,500 volt, 508 volt. Now the load current from the equation P is equal to VR IR cos phi r. So we have the value of power 20 into 10 raised to minus 6, 20 into 10 raised to 6, and root 3 into VR is 110 into 10 raised to 3, and the cos phi r is 0.9. So from that we can determine the value of IR, that is 116.6. Now the cos phi r is 0.9, so from that we can determine the sin phi r. Now taking the receiving end voltage as a reference, that we already discussed in the phasor diagram, so that's why VR is at angle 0, so that's why VR plus J0 it's 63.508 kV or 63,508 voltage. And now the load current IR as the two components, again cos phi r minus J sin phi r. So by placing the value of cos phi r and J sin phi r, we'll get the value of IR, that is 105 minus J 50.7. So voltage across capacitor, so this is the equation that we can write with the help of phasor diagram. So V1 is equal to VR plus IR Z by 2. So we have all the values of VR IR Z by 2. We can determine the value of V1, means it is the voltage across the capacitors, that is the imaginary voltage that will form across the capacitor when we consider nominal T method for the transmission line analysis. So V1 will become 65,572 plus J 1,593. So charging current IC is again Y is equal to Z is equal to V upon I. So Y is equal to I by V. So IC is equal to JY into V1. We have the value of Y and we have the value of V1. So that's why IC is minus 0.4 plus J 16.4. Now the sending end current from the phasor diagram, we can write that IS is the combination of IR plus IC. So by placing the value of IR and IC, we will get the value of IS. So that is this is the IS, 110 ampere. This is the sending end current. Now the sending end voltage means Vs is the combination of V1 plus Is into Z by 2. So we have this values V1 and Is into Z by 2. So Vs is equal to 67,304 plus J 3342 voltage. Now the magnitude of this Vs is under root of this two terms. So 67,304 means square of this, and this is the complex term means J term. So the square of 3342 square. So this will become 67,387 volt. So line value of the sending end voltage, we have this is the phase value. So it is multiplied with the root 3. So this will become line to line voltage. So 116.717 kV. So total line losses that we can determine 3I square R by 2 plus 3I square R by 2, because we are considering the effect of capacitor at the middle. So we are taking left hand side and right hand side of the transmission line. So this is Is square R by 2, and this 3IR square R by 2. So at the receiving end side is 116.6, and at the sending end side current is 110 square 110. So by placing these values, we can determine the total line losses for the three phase. So that is 0.770 megawatt. So the transmission efficiency is output is equal to output plus losses, so input. So 20 divided by 20 plus 0.770 into multiply by 100. So the transmission efficiency is 96.29%. So this is how we can determine all the parameters of the transmission system using nominal T method. So after this presentation, after this lecture, you have this assignment question. These are only the assignment question, the example related to the topic. So please note it down. And the assignment question is explain nominal T method with suitable derivation and Phasor diagram. You can take the snap of this slide for your for your assignment to write this assignment later on. So if you have any query or any doubt related to this topic, we can solve this queries or doubt in our doubt solving session. And also feel free to call me for your any query and doubt regarding this subject. And the related instructions which are written at the bottom of the assignment question. So please read it carefully and follow this instruction strictly. Thank you very much all. Thank you students. Jai Swaminarayan.